that over here, right, these are all our yield, right? This line over here is all our yield, and this is also our negative yield, or yield in compression, and the top is based on Tresca. The maximum shear is stress yield divided by 2, and this line over here is the shear stress equal to minus stress y over 2. Likewise, over the other side is the same. Okay, so this is how Tresca criteria operate, and that's how we identify the operating regime. Okay, so enough of Tresca now. So what we're going to do now is we are going to look at a particular design of a shaft that I've posted on Tuesday, the example. So if you go look at your Tuesday's uploaded the images, you should have this question. So we're going to get the question and the picture. Okay, hold on. Right. Copy. So we are looking at this shaft now, and this shaft has compound loading. Okay. Okay, so this is our example number 1. And there's a lot of things that you need to interpret from the question. Okay. The loading is easy. Okay, as I said, the loading is easy. So what you can see over here is we have a shaft that has internal loading at critical section along the steel shaft of a ship are calculated to be a torque of 2,300 pound-feet of torque. So we have a torque over here. And then we have a bending moment of 1,500 foot-pound and an axial thrust of 2,500 pound. Okay, so that is given. So now, if the U point for tension, okay, for tension is at 100 ksi, okay, you deliberately say that you have a yield in tension, and we also have a yield in shear, which they were very kind to us to calculate that the yield in shear is what, 50 ksi. So we know, right? We know that based on ductile material, okay, based on ductile material, the yield or the shear yield is equal to the yield divided by 2. Okay. Then it states determine the required diameter of the shaft using the maximum shear stress theory. Okay. So if failure is going to occur, failure will occur based on the maximum shear stress theory. So if you look at the maximum shear stress theory, if we look at what we have done last week, okay, or on Tuesday. So the maximum shear stress theory have two conditions. Okay, one is where stress A is equal to 0. You have to apply this condition where shear max is equal to half of maximum stress. Okay, where one of your principal stress is 0, or your stress max have to be half of the absolute value of stress max minus stress mean. For this case, you have at no place is that where the normal stress or the principal stress is equal to 0. So you have to apply either one of the condition. Which one to use yet, we don't know. Okay, we don't know whether to use the one where one of the principal stress is equal to 0, or you have a magnitude for both principal stresses. We don't know yet. We have to find out. Right. So from here, all right. So given all these values, so the first thing we are going to construct our transformation. Okay, so this is our y always along the shaft will be our, hey, Eugene, come on, wake up. So this will be our x, and this will be our z. Okay. So this will be your X, this will be your Y, and this will be your Z. Okay, so we have a shaft. So we know that given to us, right, we know that the stress U is at 100 times 10 to the power 3 psi, right? And the shear at U is equal to 50 times 10 to the power 3 psi. All right. If this value is not given, we also can calculate. We can calculate based on the above formula. Okay, but it's given to us, good for us. Okay. So based on the loading, all right, we look over here, based on the loading, Px is equal to minus 2,500 pound of load. The torque in the x direction, or on the x-axis, is equal to 2,300 pound-feet. And we have to change it to pound inches because our stresses is in pounds per square inch. Okay, so anything in feet, you have to change to inches. So this is 2,300 multiplied by 12. So this will be equal to 27,600 pound-inch. And then you have your moment in the Z direction, which is 1,500. Right, 1,500 pound-feet. And then this will be equal to 1,500 multiplied by 12. And this will be equal to 18,000 pound-inch. Right. So now, given this load system, right? Right, given this load system, we have to apply the maximum shearing stress criteria. So we have to apply, right? We have to apply the maximum shear stress theory, right? But why do they have to mention that we have to apply maximum shear stress theory? What's so unique about the maximum shear stress theory? Okay, so this is not a distraction. This is to see whether you understand the maximum shear stress criteria. Okay, so the only thing that's given to us is this, right? If the U point for what? Tension. They only mention the name what? Tension. Okay, why is this a problem? Given the loading condition, the axial load is running in what? In compression. So, and for this bending moment, right, at one point of the shaft, the maximum loading is going to be compression. It will not be equal to what? Tension. I repeat again, over here, our axial load is in what? Compression. Okay. Our bending moment, right, at one stage, at a single point of the shaft, will induce compression also. So the maximum stress region is not in tension. It's going to be compression because of this, right? Remember how we calculate? We calculate stress X is equal to minus, so we know this is minus Px over A. Yes or no? Then you know, we know that it's going to be plus minus mz over izz multiplied by what? Y. So for stress X to be maximum, right? I repeat, for stress X to be maximum, so for stress X to be maximum, what must happen is equal, we have to have minus Px over A minus mz over izz multiplied by Y. It cannot be what? A plus. Yes or no? It cannot be a positive. So in this context, right, the maximum magnitude the maximum magnitude will be in what? Compression. Yes or no? If you change this to plus, what will happen? The stress X, the normal stress in X direction will not be at its maximum. Okay. So now, what is given to us, unfortunately, is only what? Tension. But what did I say when we have maximum shear stress theory? So if we draw the maximum shear stress theory operating bracket, so we just constructed this earlier, okay? We just constructed this. So we drew this earlier, right? We drew something like that. Right, we drew, hey. So we drew this earlier. So we have a box. So this is our stress A. This is not Mohr circle, yeah? This is looking for operating bracket. So we have something like this. So what did Tresca assume? Right, remember what I told you? Yield in tensile is also yield in what? Compression. That is the assumption that he make. Right? So when that's the case, you declare in Tresca, so you have to understand the theory. You have to understand the operating bracket of the theory first. Okay, if not, you'll be wondering, okay, if not, you'll be wondering, okay, let's analyze the structure just based on tension. No, no. Okay, it has to be in maximum compression. Why is it possible to use maximum compression? Is because in Tresca criteria, right, in Tresca criterion, okay, stress yield in tension is also equal to what? Stress yield in compression. Right? So in Tresca, the yield in tensile is also equal to the yield in compression. So for this case, we know that, hey, we can analyze our structure in compression. We're going to use the same maximum magnitude in compression that is corresponding to what is quoted to us at minus 150 megapascal. So that's what it means. So we have to analyze the structure where we have maximum magnitude that will be in what? Compression. Okay. So yeah, a simple message like this, okay, has a lot has reason and has interpretation. Okay, so I want you all to know this. Okay, this is absolutely critical. If you don't know this statement, you say, okay, let's analyze it in tension. Okay, we're going to do this in tension. Why should we be doing it in compression? Okay, why you can do this in compression or in tension? Because we already know this value over here will be higher. Right? The axial loading usually is the what? Lower. Yes or no? Right? So if you think that, hey, the question only asks us to measure the U point for tension, you will not use this as negative. You'll use that as what? Positive. That's where the problem comes, because you're not getting the maximum magnitude. And then if you say that, okay, Eugene, we know the maximum magnitude, but what is the yield in compression? So based on Tresca criteria, we know that the yield in tensile is also equal to the yield in what? Compression. I know there's a lot of information I'm dumping at all of you now, okay? But please watch the video and listen to it, okay? And listen to what I've just said. The most important thing is this condition over here. And why we focus on what? Compression, okay? Why we focus on compression. Okay. So the next part, as I say, this question is the structure. If you look at the structure, it is really simple, right? Really simple to analyze. But the details of integrating the yield criteria with Mohr circle is very critical. And now we are going to combine our shear stress and what? Bending moment. Okay, so what do I mean by that? Okay, so now let's look at the structure again. Okay, I'm just going to copy this. Okay. So based on our transformation, I'll sketch our transformation out. This is